We are back for lesson 8.9, AP Calculus Curriculum, volume with disk method revolving around the x or the y-axis. This time we're going to do some examples revolving functions around the x-axis. We're going to have a BC example in here also, so using some indefinite integrals. This first one though will be applicable for calculus AB or BC. We're going to look at let R be the region defined is a region bound by the curves y equals the square root of x equals 1, and x equals 5. And we're going to find the volume of the solid that results from revolving R around the x-axis. The first thing I'm going to do is sketch this curve and this region. It makes it so much easier if I can see it. Square root of x equals 1, and x equals 5. So we're looking for this region is R, and we're going to revolve it around the x-axis to form solid. We're going to start by drawing one rectangle inside the region. We're revolving around the x-axis. So that means we're going to create a cross section by revolving that one rectangle around the region, or around the x-axis. That's going to form the disk. I'm going to draw that disk out here. We're going to look for the radius of that disk, which in this case is going to be the square root of x. The width of that disk is dx, and so the volume of that one single disk is pi times the radius squared, which is the square root of x squared times dx. The volume of a cylinder is the area of the base times the height. Here's the area of the base, and here's the height. So next, we're going to set up the integral. We're going to integrate all of these, and we're going to go from x equals 1 to 5, because that's the region we're concerned with. So our limits of integration are 1 to 5. We're going to pull the pi outside because it's a constant multiple. Square root of x squared is just x, and then times dx. It's a nice, pretty easy integral to integrate. So we're going to end up with pi times x squared over 2 from 1 to 5. When we evaluate that, we get pi times 25 over 2 minus 1 over 2, which is 24 over 2, times pi, or 12 pi units cubed. Sorry. Let's go to the next example. That's how we do that. Show all that work and you should be fine. Let's do another one. This time we're going to have, this is a BC example. So you can skip this part if you're in an AB calculus class. But we're going to let R be the region defined by the region bound by the curves y equals 1 over x squared, x equals 1, and the x-axis. This is going to result in an improper integral. Let's go ahead and sketch this. The curve 1 over x squared is going to look like this. The line x equals 1. And because that goes to infinity, that's where we're going to end up with the improper integral. Our limits of integration are going to be 1 to infinity. So let's draw one cross section, or one rectangle. We're going to revolve that around the x-axis to get our cross section. I'm going to draw that out here. Width is going to be dx. The radius this time is 1 over x squared. So now the volume of one cross section is pi times 1 over x squared squared, radius squared, times the height of the cylinder we've generated there, the disk. And so we're going to integrate those from 1 to infinity. Pull my pi outside again. This is going to be 1 over x to the 4th, or x to the negative 4. Let's just write it like that. times dx. So when we integrate that, we're going to have to do pi times the limit as b goes to infinity of 1 to b, x to the negative 4 dx. So that's going to equal pi times the limit as b goes to infinity of, this is going to give me, we add 1 to the exponent, divide by the new exponent, so negative 1/3 x to the negative 3. And that's evaluated from 1 to b, which is the same as pi, not the integral, times the limit as b goes to infinity of negative 1/3x cubed from 1 to b, which is pi times the limit as b goes to infinity. And this is going to be negative 1/3b cubed minus negative, so I'm going to put plus 1/3, because 1 cubed is 1. As b goes to infinity, this part goes to 0. So this is all going to equal pi over 3. And that is the volume, that's units cubed, because we're doing volume. And that's how we revolve that curve around the x-axis with an improper integral. Let's do one more. This is a fun one. We're going to derive the formula for the volume of a right circular cone with radius r and height h. And I'm going to do that. Remember, a cone looks like this. So we got the radius r and the height is h. I'm going to do this by laying this cone with that axis, or the height, along the x-axis, and the base is going to be created by revolving a line around the x-axis. So what we see is, if we take this little triangle, where this is the radius and this is the height of that cone, and we revolve it around the x-axis, we end up with the same cone. So here, this is the x-coordinate h, and this is the y-coordinate r. And so what I need is the equation of this line. And when I do that, I can draw a rectangle inside that triangle and revolve that rectangle around the x-axis to generate this cone. I do the integral from 0 to h. So I'm going to take one of those cross sections. I know we need to find the radius, expression for the radius for where that rectangle is. And we know the height is going to be dx. So how do we find the radius for one of those rectangles? Well, this is just a line. And we know that the line has a slope, change in change in y over to change in x. So the slope of this line is going to be r divided by h. And so the equation of the line is going to be y equals, it's going through the origin, so the y-intercept is 0. So the equation of the line is going to be r over h times x. So that's going to be the radius, r over h times x, for any one of these rectangles that we create inside any rectangle we create inside there is going to be r over h times the x value at that rectangle. And the width is going to be dx. So that means that this volume of this one cross section is equal to pi times the radius, which is r over h times x squared times dx. And I'm going to integrate that from 0 to h. So I'm writing pi outside again. Now I get r squared over h squared times x squared all over, no, sorry, that's times dx. We haven't integrated yet, so we're not putting it over anything. The r squared and the h squared are constants because I fixed those for this one particular arbitrary column. So the r squared over h squared can come outside, and that can become integral from 0 to h of pi r squared over h squared times x squared dx. So when I integrate that, I get pi r squared over h squared times x cubed over 3 evaluated from 0 to h. That gives me pi r squared over h squared times h cubed over 3 minus 0 over 3, or just 0, which is pi r squared over h squared times h cubed over 3. Well, the h squared cancels here, leaves me with h, and this ends up with as the volume of this cone with radius r and height h is pi r squared times h over 3. And if we go look up the volume of the cone on Google, we will see we just derived it. Pi r squared times h over 3. And so there you use that to figure out something that the ancient mathematicians did before they had calculus. But calculus confirms that that is the volume of the cone. And that's part 2 of our 8.9 series.